Let me check. Yes. Yeah, I hope my screen is visible to all of you.
Yes, sir.
Okay, thank you. Okay, yeah, so today I would like to start my presentation with the two parts. So one is single crystal growth and its applications. After that, I will take a small break and then give a brief overview about their characterizations, like structural and one of the physical properties, like magnetic and
Sir,
so
please
on.
wait, sir.
Yes, yeah. Hello.
1 minute, sir.
Uh,
Sir, you can continue, sir.
okay, thank you. Yeah. So single crystal growth and applications. So plan of my presentation is as follows. First, I would like to define what is crystal and then single crystal. So once you see the difference between the single crystals and the rest of the crystalline materials like polycrystalline and nanocrystalline and amorphous, then we will see why we should do, what is the importance of the single crystals, how they are drastically different from that of the other materials in terms of exhibiting the exotic physical properties and the applications. Okay, so herein we will discuss we will just flash out some of the industrial applications of the single crystals and also current frontier research, how crystals makes very big impact on the research and so on. Okay, so then after explaining these three elements, then in the next talk I will give their characterization tools, particularly how to characterize the single crystals like X-ray diffraction or live diffraction, and then scanning tunneling microscope, one of the microscopy technique. We will go through them, and then after that physical properties like maybe magnetic and heat capacity and so on. Okay, so in the first part, so first I would like to start with some elementary question. What is crystal? So yeah, a very simple and straightforward answer is that it is a set of crystal contains a set of atoms, and those atoms are arranged very periodically. Okay, so you will see very regular repetition of the some set of atoms. You will see them, that is called unit cell. And also how long these unit cells are ordered, so infinite. So this is a combination, simple definition. It should be periodic, and then they should have a long range order. So combination of periodic and a long range order both exist, then you can say it is a crystal. So, and there are different types of crystalline materials are there. One is single crystal type, and then polycrystalline, nanocrystalline, and amorphous. Of course, amorphous is not a crystalline material, but based on the size of the, just to give you an idea about its size and its how it is different from crystalline material, I just shown here. Okay, single crystals. So typically their size is much. You can touch them, you can feel them, few millimeter greater than few millimeter size, and their size can extend until several meters also. And then polycrystalline samples, they are almost like a kind of similar to that of crystalline material only, but they have a grain boundaries. You can see the schematic diagram of the single crystal and polycrystalline sample. So in the single crystals, atoms are ordered and they have only one grain boundary. So in between any part of the crystalline material, there you should not see any kind of boundary. So boundary you will see at the end of the size of the crystal. On the other hand, polycrystalline samples, it is again crystalline only. You would see long range order and periodic, both of them. But there is a breakage of between the different constitutes. Like you can see this is oriented in one direction and this guy is oriented in another direction, like that way polycrystalline samples. So like similarly nanocrystalline and amorphous also one can distinguish. So their sizes are millimeter size and micrometer, and nanocrystalline material have some nano, a few angstrom units. So amorphous materials are not belonging to this category because they have neither periodic nor long range order, but they have rather short range order. That short range order, few angstrom units, maybe 2 or 3 unit cells, until 2 or 3 unit cells, they may have a short range order, but after that they lost their long range order. Okay, so now after once you understand crystalline material from our high school definition, then single crystals. So I hope most of you might have seen the single crystals. So the single crystals have a like a crystal structure is continuous. So you will see here single crystals are shown here. One thing immediately you will see that very sharp, shiny, cleaved surfaces you could see them, and each surface is really a one Miller plane. So if you can see here, this is Miller plane of 100, and this face is 112 and so on. So that means you can see the directly such a kind of Miller planes with our naked eye. So and so why we are very much interested about the crystals and everything, it is that it doesn't have any grain boundary. So it's a single grain boundary element, and you do, because of that there will be no more defects due to the boundaries. So that means it has a very unique two properties exhibits, like electrical, magnetic, and transport and so on. So very ideal properties one can prove. And another important thing is that they are anisotropic. So since you can see different directions, 100, this is one of the crystallographic direction, and 110, this is another crystallographic direction, 111, and so on. These are all Miller planes, but there is no guarantee that these properties along this direction should be same as this direction. So there can be a drastic difference between them. So in that way, one can tune the optical, magnetic, and electrical and transport properties as they have a clear directional dependence. So this gives the opportunity to, by changing the orientation of the crystal, one can tune the physical properties as well. So industrially, it has plenty of applications. So as you all of you know, in your hand you might have mobile, so which is without silicon, so we don't have this much technology and so on. So this most of the technology what we are enjoying, this is all coming from, we are in the silicon age. So almost all devices, your computer, microelectronics devices, and microprocessors and memory devices, and almost all of them are, those devices are printed on the silicon wafers. So the silicon wafer is nothing but a single crystalline material. Okay, so now we our real world is very much connected with these single crystals and so on. So we will see how these single crystals are grown, and what are the different kinds of methods, and for each method there will be pros and cons. So we will discuss some of them. Okay, first, single crystal growth can be made in various ways. So one is melt growth. So you can have a solid sample, just melt it, and using some variety of techniques, one can pull the crystals out. That is one method. Second technique, you just dissolve your desired material in a solution, and then just follow some sequence of steps by slow heating, slow cooling, and so on. You can get the crystals from the solution also. And evaporation technique, something like a chemical vapor transport, where you can you don't have to melt the sample, you don't have to dissolve. There will be a transport agent, that chlorine or iodine, that material will carry the one by one some part of the sample it carries and deposit in some other end and forms like a crystals. So there are three types of broadly one can say crystals can be grown, and let us discuss one after another. So first one is melt growth. So melt growth means you must have a container, so where you can melt the crystals in a small crucible. So that is one method, and without crucible also one can melt. Okay, so first method is with crucible. One of the method we will see. So one is Jokrowski method. So this first Jokrowski method. So in this method, so what people use it to do is that they melt the crystals. For example, silicon. So the silicon one can melt. So when it melts like a congruently. So congruently means some elements after melting it won't lose its crystal structure. So some that is those are the category of the congruently melting crystals. For example, silicon, one can prepare the single crystals in our laboratory also. Just take a elemental silicon, just melt it and slowly cool down, you will get single crystals, but very small size crystals, and it's not that much of the high purity crystal one can get in our laboratory. But industrially they do have a kind of process to grow almost very perfect ideal single crystals of large size. Okay, so in this for growing the single crystals of the silicon, this one of the famous technique is Joklashi method. So in this technique, so one needs to melt the crystals like this way. So whatever silicon, elemental silicon, that is getting melted in this form. So once it is melted, it is in the liquid form. So when it is in the liquid form, then choose a some seed crystal, just dip inside the this melt, and then slowly pull out. So when you slowly pull out, then you can see you can see the crystals are coming along with the melt. So from the liquid form, this, so you can see liquid level is getting decreased eventually, and a single crystal is coming out. So this is the one very efficient way of growing the large size crystals. You can see the size of the crystal. So it is almost like 2 meters of the crystal. This is industrially people use it to do, like where most of the fab labs, like Taiwan manufacturing semiconductor unit, Taiwan, or many places like Intel. So all these big companies, they mostly have this crystal growth technique. Okay, so this method, there is a cool make the metal into the liquid, and liquid you are cooling the liquid slowly and pulling the liquid slowly and making the crystals. This is how you can make the crystal. So how slow you have to do? It's very slow, like a 1 millimeter per hour. So that means in a day you can pull only 2 centimeter crystal. Okay, so if you wanted to grow this 2 meter, you have to wait for several days, like nearly 100 days you have to spend, and then only you will get 2 centimeter size crystals. So like this is how crystals are grown using Joklashi method. Okay, and so this it has limitations also. So one is you cannot grow the crystals where it will release the vapors very badly. Suppose if you melt any material, so some materials get volatiles very easily. So that kind of crystals are not applicable using this method. So it should be, if you make it liquid, it should be remains like a liquid almost. So such kind of materials only can be grown using this one. And so there is always a possible contamination from the crucible. So because you have to, when you are using such a large size crystals, you have to melt them in some crucible. This is the crucible. So this crucible is also nothing but some chemical element, aluminum oxide or platinum or whatever. So preferably they use the oxide type of crystal for melting the metallic type of elements. So then there is a possibility, always a possibility of the contamination with the crystal surface with the container. So that we cannot avoid. That is the one drawback in this technique. But however, it has advantages. The pros are much larger than these cons. So one can grow very large size crystals. Otherwise, who can help in growing such a large size crystal? So this is using this technique. Although some impurities are there that can be handled somehow, but large size crystals in order to grow, this is only the technique. And another way is that if you wanted to dope any element, for example, you wanted to prepare silicon. Instead of silicon, some n-type or p-type silicon if you want to do. So some arsenic or phosphorus you want to do element. So this is the best element. You can melt along with silicon some more phosphorus, arsenic, whatever desired way you wanted to do. You can melt them and pull out the crystals. So like that way you can prepare a variety of crystals. So and you can control various preparation techniques so that you have size of the crystal, orientation of the crystal, everything will be in your control. Okay, this is a one type of technique where most of the industries are using this technique. Okay, so this is the typical furnace in the laboratory. So it's a small size furnace where one can keep the graphite crucible. In the graphite crucible, one can melt all this silicon and pull one after another. And so these are the wafers. So once you have a single crystal of this much size, one can cut them into small plates. These are nothing but wafers. On these wafers, all our the microelectronics chips and all are installed over here. Okay? Here one grow the crystal with a very slow pulling. So like here you don't have to have a seed crystal. Suppose if you don't have seed crystal, then very difficult to grow that Joklak method. So what if you don't have any seed crystal? So this is another technique, Bridgman method. So in Bridgman method, the furnace is designed in two ways. One is this is high temperature part, this is low temperature part. Okay, this is a high temperature zone and low temperature zone. Let us say this is 800 degrees, it is there, and low temperature, let us say 700 degrees, it is there. Suppose if you have a material of 750 degrees of melting point, so you can set these two temperatures of the furnace. One is at 800 and another is 700, and place whatever desired material in your crucible. So this crucible is made like this way. So one important feature of the crucible, you will see that very sharp crucible should have a very sharp end. So why it should have a sharp end? Because when you melted the crystal, so sorry, when you melted the crystal, you should have some nucleation. So in the previous case, you have some seed crystal. Okay, seed crystal will take care about pulling its oriented crystal. But here you don't have seed crystal. You just have to start from the beginning without crystal, without any seed crystal. You have to start. That means to begin to grow the seed crystal, very sharp edge will help. Yes, help significantly. So at the sharp edge, so it is very easy to start the nucleation. So crystallization process, and at this end, it is very easy to start. That is a sharp edge crucible is used here. So in this sharp edge crucible, pour the whatever desired polycrystalline sample or a metal, whatever you want, you just pour it and melt it. If the material has 750 degrees, go to 800 degrees and slowly cool from 800 to 750, something like this is 800, this is 700. So 800 to 700, you just pull this one pull from one zone to another zone very slowly. Again, here speed of this crucible should be 1 millimeter per hour. So very slowly you will have to pull from one end to another end. So when you do this one, so you will see at the end this kind of crystals at the end. So you can see the sharp end. This is where crystal is started, and it started increasing this way, and then it continues. Growth process has once it is started, then the proper orientation it will take its own way. So there is no control with us what orientation it should be taken. So because it's we did not start any, we did not give any input, just based on its crystal structure, based on its material property, it will choose its own orientation. Okay, like this way. You can see here, you can see very cleaved surface here. So this is the one surface you can see. So this, you can almost, it behaves like a mirror. You can see your face and so on. Okay, so this is the way such a large size crystals, like you can see here 10 millimeter size crystals, more than 10 millimeter size crystals you can see over here. So this is another type of crystal growth technique that's called bridge method. Okay, so third method is solution method. Like it is exactly how this sodium chloride crystals are made at any one can do in our kitchen also, this kind of crystals. So here what you need to do, you have to choose a starting material, and that material should be dissolved in a solvent, that means flux. So here it's very easy and cheap technique compared to other two, because here the pulling of the crystal for 1 millimeter per hour, you should really require a very good furnace which controls this movement. Okay, and this industrial furnaces also is very bit expensive. Okay, so we don't have that kind of crystal growth facility anywhere in India. So because it's all related to industry related stuff. Okay, but in this flux growth things one can do in our laboratory even. So here what should be done, here crystals you can dissolve in a flux, like for example sodium chloride you can dissolve in the water in the similar way. Sodium chloride is your desired material, water is your solvent or flux. So once you dissolve, so first property, that material should have a solubility nature in the corresponding flux. That means you have to choose the flux in such a way that that material should be dissolved. Okay, example water and sodium chloride. And then these crystals, once you dissolve, then add more and more amount of the material in such a way that you will reach the supersaturation. Okay, so this is another important point. So one is dissolving, and there is reaching the supersaturation. So once it is reached supersaturation, then cool down the material or crystal, whatever, then you will at the end you will get the crystals like this way. Okay, this is just for fun, I have shown some candy, but it's really crystals can be grown. Okay, so again just to repeat, you have for example you take any sodium chloride, it has melting point nearly 750 degrees. Is it possible to melt 750 degrees in our normal weather? No, possible. It is not possible. But still, you can prepare sodium chloride crystals even at 50, 60 degrees even. How? Because you are mixing the NaCl plus H2O. That means you are reducing the melting point of sodium chloride by water. Okay. So it does, and at 1600 degrees temperature to grow the chloride crystals. Okay. So this is one simple example for the flux growth method. Okay. And then another important method is hydrothermal technique. This also can be done in our normal laboratory. You just need only either furnace or oven, and then some kind of very small Teflon type of container. And in this container, again we use the purely water, and that material should be dissolved in the water at high temperatures, and high pressure, both of them actually. So high pressure means So it's like a water pressure. So maybe 3 MPa pressure will be at something like 220 degrees. Okay. So under the small conditions, minimal conditions, one can able to grow the crystals using this hydrothermal technique. Okay. So of course, so there are a few more techniques are there, like a hydrothermal only, but high pressure techniques. But those high maintaining the water pressure vapor at high temperatures more than 250, that containers are not available. One needs to use external pressure in a normal steel body only. So one can generate the high pressure and one can do this kind of crystal growth under different kinds of temperature conditions. Okay, so this is another method. So this what I have shown in the beginning. Let me show the picture again. Here we have shown different varieties of crystal growth method. So one is with crucible. So Joklashi method and Bridgman method. These two we have seen. So these two methods helps to grow the large size crystals. Okay. On the other hand, solution method also we have seen hydrothermal and flux growth method. It is a little cheaper technique. So, but however, you can get the very good quality crystals, but very small, medium size and small size crystals only you can get over. Okay. So how to avoid this container? Is a technique without using container also one can grow the crystals. That I'm going to discuss now. To using container, without using one can grow the very large size crystals. That is optical floating zone. Okay, so optical floating method I bring over here. So for optical floating zone method, you need to make your desired sample, polycrystal sample. To so this material what you do is called feed rod. And same similar type of rod only you can make in the seed rod. Okay. So the seed rod and rod these are lying one another. So what one can do is that you can melt the rod over here. Okay. So if you melt liquid, this liquid due to the surface tension, that liquid lies in between the two rods. Okay, so interestingly, this temperature, so this temperature will be, so I can reach using this kind of floating zone furnace, 2000 degrees one can reach. Okay, at this temp, the rest of the element will be at room temperature. Okay, this is a very local heat. So only at this temperature only you focusing release the light because of the reflex. All the light concentrated in place, it's heat of apple. Okay, one can go 40 degrees also with this kind of operators. So, but safe 1000 degrees. So, can control whatever. Suppose your sample is at 100 degrees, melts. Use the lamp power such that it melts at 100 soon. That everything is in your control. Is the melting point of the material. Slowly figure out do whatever to 2000 degrees. So any type of crystals one can be able to this using optical floating zone. You can see the crystals grown using this floating zone method, very large size. You see almost like a 10 centimeter size crystals, 10 centimeter long size crystals of different varieties. Some are superconductors, some are colossal. This is example. It is a so different varieties of crystals one grow with this kind of floating technique. So this is about the uh, uh, only techniques only. Many more techniques are, but broadly I thought in this presentation have the idea that crystals can be grown in various ways: melting, dissolving, by transportation of the using some transport agent. One other end, one can transport one after another and deposit somewhere, get the crystals, and so on. So these are our crystals now. Now, let you have questions on these three topics, then before going to the application. So, yeah. Any question? So, no, no questions. And I will go ahead and uh, someone right. So,
Sir, excuse me.
yes. Hmm.
Your voice is double break, sir.
Is it now? Hello.
Okay. Okay.
Yeah, I will hold here and talk like this. Okay? So, but I would like to, I mean, they should go to the next or any questions from the audience.
Sir, from the end of the session, I will some
Okay.
whoever it will asking the question chat box
Okay.
at
Hmm.
that time only I will ask. Sir.
Okay, perfect. Okay. Now that next I am going to go to the most interesting element. So these applications, why should we go this crystal too much? So this is the, so some of them are very day life we have been using them. For instance, any gauge, either screen or any microelectronic device or anything. So everything for father of all of them is nothing but silicon. So in the whole periodic table, so how many semiconductors are there in a whole periodic table? We have only two. Okay, rest of them are only metals. Okay, it's very surprising. We have nearly 104 or 108 periodic elements are there in the periodic table, but only two are the semiconductors. One is silicon, another is germanium. Only two. But out of two, silicon is the one where we have been using this one heavily. So it is it has so high abundant in such a way that we never get any kind of shortage of silicon yet. So that means silicon dioxide, that sand everywhere we find. So from the silicon dioxide, after removing the oxygen atom, it becomes silicon, elemental silicon, and by processing elemental silicon, and eventually you are getting the crystals, and from the crystals you can get the wafers, and from the wafers, on the wafers you are making these microelectronic circuits. So from these circuits we are getting the mobiles and devices and so on. So this is the father of our current modern technology, this silicon. And this silicon crystals can be grown using these two techniques: Joklakshi method and floating zone method. These two methods we have discussed in the previous two slides. Okay, so this is in Joklakshi method, you melt and you take some seed crystal and pull it, you will get this kind of very big, large size crystals, silicon crystals. So we are fortunate that we have only two semiconductors. Out of these two semiconductors, we have enough abundance on for the silicon, and that is congruently melting. What if after melting, if it is no more silicon, then it's a troubling thing. We might not have this much technology. So this how nature helps us in getting the large size crystals also. So unless nature supports us, we don't have this much technology also. Okay, this is the silicon wafers. On these silicon wafers, so electronic circuits are built in this way. Okay, so yeah. And another thing why we should look for the crystals only, as I said you earlier, so we have to the most of the physical properties depends on what is the size of the single crystal. Because if you have a very infinite size, then there is no grain boundary effect. So then that properties are quite different. If you have a, so if you have crystals with bad quality, like polycrystalline samples, it won't be applicable anymore. Okay, so that means that is why this micro fabrication labs, they put a huge amount of efforts in growing the high quality and large size crystals. Okay, especially silicon and so on. Okay, so, and another silicon is not only useful for this current electronics. It is heavily used for several other things like photovoltaics, like solar cells, and many optical properties also it has been used. Okay, so not only the silicon, there are many other semiconductors, but those are not elemental semiconductors. Like elemental semiconductor means silicon and germanium only, these two only. But one can synthesize the semiconductors inside the laboratory by mixing the two elements. So that means compounds. These are compound semiconductors. For example, gallium, third group element. Arsenic is fifth group element. Third group and fifth group element, 1:1 ratio. If you take gallium arsenide compound comes out to be. This is a compound semiconductor. So similarly, second group and fourth group, sixth group. Okay, second group and sixth group also makes the this kind of combination semiconductors. So what is so special in these compound semiconductors? This most of the semiconductors with the compounds like a gallium arsenic and INP and so on, most of them having direct band gap. So when you have direct band gap, then it is easy. It have a plenty of more applications in terms of solar cells and photovoltaics and so on. Because you whatever energy you are giving to the valence band electron, it will directly shoot it to the conduction band and it will produces the electricity and so on. And this since this is made like a elemental superconductor, it can you can dope and you can tune the carrier concentration n value or type of the carrier concentration also, like a p type or n type. So whatever the way you want, you can tune about them compared to indirect band gap semiconductors like silicon, for example, it has indirect band gap semiconductors. So these compound semiconductors have their own applications. So these crystals also have one can grow using the bridgman technique. So this bridgman technique also I have shown in the previous one. And another type of important material of current interest is graphene. So most of you know this graphene has large carrier mobility and high thermal conductivity. So this is very interesting material, uh, but application point of it still under the topic of research. This single crystal graphene, because graphene can be, if you can able to grow the graphene single crystalline graphene and a very very big, then it can be used for the use of application much better, as it is exhibiting much properties than silicon in terms of conductivity and conductivity. So it has used in many other devices, but it under the research in growing the large size crystals. Okay, so one of the challenges to grow the high graphene over the using this tactile techniques. This a kind of interesting research modules in type of crystals. And another type of crystals are organic conductor crystals. So these are useful for flexible electronics. So you can hold, right? We can like how you are folding. Same way you can hold your mobile and keep it in your pocket convenient place. It can be carried anywhere. So that to make that kind of one, so like semiconductor crystals will be highly useful because they have a flexibility of holding them and so on, but they have their own challenges. So like these organic semiconductors have high vapor pressures while growing the crystals, and although they have a low melting point, but making them making sustainable crystals for a long time. In kind of weather, they should be able to survive and so on. These kind of crystals are still under the of the research. It's okay. So this is one thing. Okay, optical part. So transparent in visible light, but it is transparent in the infrared wavelengths. So that it used for to controlling some kind of wavelengths, some kind of wavelength like that way. So we use as optical windows, and summer is a nothing but AL23. So this AL23 crystals be used for detectors, like X-ray detectors and X-ray detectors and the research on this material, the quantum technologies, where we can able to this material should be at some point should be used to build quantum computer like superconducting quantum uh, devices, something like that. Okay, so where you have where at present your computer can able to uh, tune the bits like ones and zeros only. But once you have a computer, you will be able to tune. You will be able to play with these qubits. It has multiple possibilities there, not only one and zero. Any combination of one and zero should be a bit that can be that can enhance the computational. On the other hand, this crystal has been is a current any kind of material science or as metaphysics. Their starting point should be the crystal. So without they can able to be concluding results also. Recently, you might have seen in newspapers or anywhere, there is a room temperature superconductivity material called LK99. L and K are the that Korean scientist names. What they have called is that this is the LK99 is nothing but PB9 Cu P6O25. This is kind of material one can prepare in any laboratory also. So what they have done, they prepared this material and they have seen some kind of magnetic levitation. So this is a polycrystalline sample. When they see this is levitating on this magnet, then they concluded that is a kind of new room temperature superconductor. Then it become a very big news in a like scroll down in the newspaper and social media. So there is a room temperature superconductivity has been found, but on the other hand, to confirm the existence of superconductivity, this polycrystalline sample is not the main element. One should grow the crystals immediately across the groups in the world. So they have simultaneously they have efforted in growing the crystals and confirmed that it is a bad insulator. So very superconductor, very insulator. So there is a huge um, discussion between these two results. Okay, so still this is a topic of debate whether this LK19 is a superconductor or not. So still a few groups are claiming that there is a possibility of having superconductivity here, but many groups confirmed that it is not a superconductor. So this is all recent 2020 and only. So this is from this what one can understand is that crystals are very much essential in concluding the fundamental research as well. Okay, so this is with this I will thank you all so for the first part of my presentation. Okay, so if you have any questions, please feel free to ask me before going to the uh, next session. Any questions? Is my voice is okay? There was some break. Is it okay now? Hello, Shivaya garu.
Sir, tell me, sir.
Yeah, is okay. So any questions from the audience?
Still now, no question, sir.
No question. Okay, thank you. So then I will go to the next part. Okay, so characterization tools. So before going to the characterization tool, so just I would like to show some of the things like see, so far we have learned various methods of growing the crystals and their applications of in the day-to-day life, and there is a plenty of scope in terms of research in growing the new crystals and studying the real-time physical properties. Okay, so and so on. Now how do we characterize them? So here few things are there. One is one of the very beginning and old technique, that is law of diffraction. So here you can see this is the Laue diffraction operators where you can mount crystal somewhere and pass the X-rays through the crystal, and at the end you will see a image. That image looks like this way. This is nothing but Laue diffraction. This by analyzing this Laue diffraction, one can able to estimate the uh, structural properties of the crystal, at least what kind of crystalline magnetic plane it has, and one can identify the suppose you expose the crystal to X-ray, and it will give you some image like this manner. Okay, so then what kind of plane you have exposed, that can be identified using this Laue diffraction. So for example, beginning these are the crystals and they have different phases, and these phases are named with 100 and 112 and 220 and so on. So how these names are given? So this how someone has concluded that this is 100? It is nothing but Laue diffraction. So when you expose this surface to the X-rays, X-ray produces the diffraction pattern in this manner. Okay, so this in this way you will get this diffraction pattern like this manner. So by analyzing this diffraction pattern, you will be able to conclude that that surface has 100 Miller plane. Similarly, if you change the crystal plane, you will be having different pattern. So that means there is a unique diffraction pattern against that corresponding HKL plane. Okay, so this how this real plane
Sir,
has
excuse me,
connected.
sir.
Yes, yes.
Slides are not moving, sir.
Okay, okay. Yeah, let me just share one more time. Okay. No, I have just let me close the sharing and again show here. Yes. Yeah. Now you can see the slides.
No, sir.
No.
Now
Okay.
it's okay, sir.
Now it is okay, na? Yeah. So how this Laue diffraction and how the real-time crystal structure both are connected each other, that we are going to discuss now. Okay, so now let me share the let me close and open another PPT in the for the second part of my talk. I have in fact three parts. So second part of the talk is this one. So this title of the talk is X-ray diffraction and reciprocal lattice. So I hope all of you are familiar with these two names. One is X-ray diffraction and reciprocal lattice. So we will go through the details of the X-ray diffraction and how it is connected with the reciprocal lattice, and these two practically how these two are connected each other we will see. Okay, before beginning this talk, I wanted to ask one question. What is the size of the typical crystal? Suppose, for example, a typical crystal structure. Suppose you unit cell. You have simple cubic unit cell. You can see here. In this unit cell, you have at every corner there is one atom, and there is a distance between two atoms that is called lattice constant of the simple cubic structure. What is the dimension of this uh, typical dimension of this unit cell? What is the distance between these two atoms? So can anyone guess? So it's a few angstrom units. Let us say 3 angstrom units. So 3 angstrom units means 0.3 nanometers. Okay, such as very small. So to probe such kind of 0.1, some decimals of the nanometers, there is no direct probe to measure such kind of small distances. However, we could able to estimate very accurately if you go and see the real dimensions of the sodium chloride or anything. So they will report like this way: 3.456 angstrom units. Okay, that means it is not even 3. 0 point, they are showing the accuracy of 0.001 angstrom units. Okay, so that means 10 power minus 3, okay, angstrom units accuracy it is showing. How it is possible? So that means 10 power minus 15 meters, I think 12 meters. Okay, so how it is possible? 10 power minus 12 meter, nobody measures it physically, no microscope, no any kind of resolution, so nobody that much accuracy. How it is done? So this is all done is not by direct measuring them, it is by analyzing the X-ray diffraction. Okay, so this analyzing the X-ray diffraction, how this so that means X-ray diffraction, it is a very important tool to understand the microscopic picture of these materials. Before understanding any property, we must know what is its crystal structure, what are the atoms it is having, where those atoms are located in the crystal structure, what is the typical distance between atoms, bond angles, bond lengths, and their interactions. Before understanding the microscopic picture of the solid, no point in understanding this whole technology. So no meaningful, no completeness. Okay, so that means it is very important how this distances and display, bond angles, bond lengths at the atomic level, and their accuracy, how those are determined, and so on, have a very significant interest and very significant importance it has in condensed matter physics and material physics. Not only material physics, biology, and so on, any kind of one. Okay, so now how this here we have simple cubic structure. Here you have BCC structure, FCC lattice. How these lattices structures are determined using the X-ray diffraction. Typically, X-ray diffraction pattern shows like this way. For simple cubic, you can see here the plenty number of peaks one can expect. Whereas BCC, so there is a limitation. All peaks will not appear like that of simple cubic. So only fewer peaks only showing. For BCC, for FCC, even fewer. For diamond lattice, even fewer. So you can see there is a huge difference between simply almost all are cubic lattices only. But despite having all our cubic lattices, simple cubic is different from BCC, is different from FCC and diamond lattice. So that means, whatever crystal structure, so you have that crystal structure have a very good connection with this X-ray diffraction. So that means that X-ray diffraction is a unique blueprint of the crystal structure. If you know crystal structure, you can calculate the X-ray diffraction, or if you have a X-ray diffraction, you can determine the crystal structure. Vice versa can be done. So both are very mutually each other, and both are very well connected each other using the Fourier transformation connection. So how those are connected each other? So real crystal structure has direct space, whereas your reciprocal lattice, that is nothing but the Fourier transform of your reciprocal lattice having indirect space, like a inverse space, reciprocal space. This inverse space is nothing but the X-ray diffraction. So these both are almost equivalent to each other. X-ray diffraction and reciprocal both have the same meaning. How these two are how these two are connected each other, that we are going to have in the discussion in the next few slides. Okay, so before beginning, I just wanted to show a some kind of simple X-ray diffraction experiment what you might have been doing in our high school optics experiment. For example, you have some arrangement of atoms are there. So this is like a kind of double slit experiment. So you have some arrangement of atoms. Okay, you have one dimensional array of atoms. You have very well ordered lattice. So when you pass some light through it, how after this light is passed through this one day array of atoms, how they transform each other, there will be constructive and destructive interference, and where you have this wave after this passing through the slit, then constructive interference causes this bright lines, and destructive interference causes this dark space. Okay, this is how you will have a dark and bright kind of lines you can see there. It's almost like a kind of grating. So if you pass the light through the grating, you will see this kind of diffraction. So because here diffraction is happening because the size of the slit between two atoms, for example, so the size of the slit is equivalent to that of the wavelength of the light, then there will be that the diffraction condition will be satisfied, and that produces the this kind of diffraction pattern. So this is what we have seen in our optics experiments. Okay, for example, grating experiment. Now what I would like to do is that I wanted to extrapolate lattice. Instead of 1D, I make it 2D. So in this 2D lattice, if I pass the light through this 2D lattice, then you can see very nice pattern, diffraction pattern. This is nothing but diffraction pattern. Okay, pattern you can see. One similarity you have seen here, spacing is small, here spacing is large. Here is a square lattice. Okay, diffraction is also square type of lattice. Some connection is there. Okay, so that means your direct lattice and your diffraction has some similarities. So you can see from the previous slide also, you have 1D array of atoms. 1D array of atoms, how they are nicely arranged, the diffraction light patterns are also very nicely arranged. Okay, that means there is a nice connection with your direct arrangement of atoms and diffraction pattern. Okay, so now let me go ahead and try to play with this lattice a bit more. Suppose if I extend the lattice space. Okay, previously you have a very squeezed lattice. Now you have an expanded lattice. Okay, so you are expanding in this direction as well as in this direction. When you expand your direct lattice, okay, that direct lattice means your arrangement of atoms you have changed, you have expanded it. Then you can see the diffraction pattern, how it appear. You have seen a closed way of arrangement of the light spots. So earlier you have a wide arrangement. Okay, when you have a squeezed lattice, you have a wide arrangement of lattice you have. But when you expand the lattice, yes.
Sir, excuse me, sir.
Yes.
The slides are not moving, sir.
So can you tell me in which slide you are this one, for example, see, I think can I see the now slides? Hello.
Sir, no, sir.
um no, from my side it is, everything is clear. Can you tell me which slide you are in now?
Reciprocal lattice, sir.
No, I'm in reciprocal lattice only. So this
Sir, please change another slide, sir.
I change it now. Is it okay?
No, sir.
You changed. No. There is a different same reciprocal lattice only, but there are 10 slides are there. Can you see slide change now?
No, sir.
Okay.
Now it's okay, sir. Now it will be changed.
No. Actually, it's not about not changing. So I will show you all of them one more time. So all
sir.
slides are similar. Very small differences are there. Okay,
sir.
I am really changing the slide. So, but there is a small variation. Okay, for example, I will show you again. So I will close it again and again open. You can see my screen, right?
Now it's visible, sir.
See, for example, you see, this is one slide. This is another slide. This is another slide. All slides are similar each other. Okay.
Okay, sir.
That is the reason. I am changing the slides. Okay, I am explaining one after another. Okay. So
okay,
here, when you have 1D array of atoms, you can see a lines of diffraction. When I have a plane of atoms, you can see the spots on the screen, diffraction pattern here. And then when I change the dimensions of my direct lattice, there is a change in the dimension of the diffraction also. But there is a very clear connection between our direct lattice and diffraction. So, and the diffraction is also very much, that connection is also very clear. When you have an expanded lattice, you have a contrasted diffraction. So, for example, when I squeeze the square lattice in one direction, then in that direction you have in the same direction you have a expansion. Okay, so like that way you could see a very clear reciprocal nature between the direct lattice and diffraction. So that reciprocal nature is associated with the diffraction is called reciprocal lattice. Okay, so this how reciprocal lattice and X-ray diffraction are connected each other. So it's in a simple layman language, reciprocal lattice of the direct lattice is nothing but X-ray diffraction. Okay, so this how X-ray diffraction and reciprocal lattice are connected each other. Now you can see the how in the reciprocal lattice, these are the different points in the, these are the points in the X-ray diffraction. When you do Fourier transformation to this one, then you can see the real time uh, densities, atomic densities you will get. These atomic densities will are nothing but the crystal structures. This is how crystal structures are determined. Okay, so this is the and now if this is all about the X-ray diffraction. So what we learned from X-ray diffraction, so this X-ray diffraction is a very important tool in determining the structural properties of the crystals. Like you can estimate the distance between two atoms very accurately until 10 power minus 12. It is because reason is that you what that real crystal structure, that means those distances are, we are dealing in the reciprocal lattice. For example, you have 1 angstrom unit distance. So 1 angstrom unit distance, okay, 1 angstrom unit means 10 power minus, let me write here, 1 1 angstrom unit means 10 power minus 10 power minus 10 meters centimeters in so it is difficult to see this kind of dimensions in the microscopic way. But what if you do the experiment in a reciprocal way? So suppose 1 over angstrom unit kind of way, if you do the experiment, then you will get 10 power 10, something like that. Okay, this can be easily estimated. So by estimating, by measuring this fellow easily, you can able to calculate the corresponding direct space, this one. So this is an X-ray diffraction. Basically it measures in terms of one can using can get this microscope picture. This how this how crystal structure and reciprocal lattice and Fourier space and all these are all interconnected each other. Okay, so now, but this is a by kind of indirect technique. So but it will be good if you can see directly the atoms, if you can measure them directly, that will be better. That will give you a better feeling than measuring the X-ray diffraction and analyzing the X-ray diffraction and say that this is the distance between two atoms and this is the type of unit cell and so on. So if you can see directly those crystal structures, that will give you a wonderful feeling. So can we see this kind of atoms really? So that is the answer, that is a question. So that is possible, but not in the very high resolution way. So one can probe the atoms using scanning probe microscopy. So this is a microscopic technique that images the surfaces. It won't image the full crystal structure, but at least the surfaces it images. So this is a this works based on the piezoelectric effect. Okay, so this how it will work and everything we will discuss over here. So this is a scanning tunneling microscope. So purely works based on the quantum mechanical principle, like quantum tunneling. And this work for discovering this scanning tunneling microscope, there has been one Nobel Prize awarded in 1986 to these gentlemen, like Professor Rohrer and Binning. So these two guys from the IBM Zurich, they have got the Nobel Prize in 1986. So now let us look into the principle. Okay, this scanning tunneling microscope. So here in this scanning tunneling microscope, it's like almost like a one how one blind man walks on the road. If you can sense, same way it will works. So this blind man, he doesn't have any more way of seeing the real world. Then he used to hold a stick. He senses with the stick and then see uh, whether whether everything is whether there are any obstacles for his path or anything. This is how he will find out by himself and walk around the things. So similarly, so when there is a kind of sample. Okay, this is the sample surface. Okay, and this is the tip end of the there is a kind of probe is having the tip. So this tip is helping to see the surfaces of the crystals and so on. Okay, so now, yeah, how it works, it is as follows. Okay, so take a sample, so very smooth surface, and then the tip is attached with the piezoelectric sensors. Then you apply the electric field between the sample. So to the sample you can give the negative voltage. Okay, and to the tip you can give the positive voltage. Then what happened, sample is having, let us say, electrons, and the tip is biased with the positive voltage. There may be a chance of tunneling between the sample and this tip. So this, there is a tunneling current happens, although they are not touched each other. You can see here, this is the sample and this is the tip. So this microscopic picture you can see here, and they are not touching each other, but the information is carrying from the whatever information of the surface that is carrying to this tip. Okay, so there are different ways of probing the this technique, like keep the constant height between the tip and the sample. So that is one way, constant height method one can do, or set the constant voltage between them in such a way that it maintains always that constant voltage. Accordingly, whenever this tip senses the more potential, then it will move, because if you set between the tip and surface, so let us say you have kept 5 volts, so that means it should always senses the 5 volts. Suppose suddenly it has seen the atom, then obviously it will senses more voltage. Then again it will, whatever voltage it has taken, then it will adjust its height accordingly. So always maintain the same kind of voltage difference or height between them. This is how the tip will move across the sample from here to here, like this way. So the, if you look at the surface is like this. So suppose surface is like this, how the tip will move. So tip also will moves in the same way. So like this way, like this way only it moves, because it has to maintain its constant height and voltage. This is how the surface of the sample can be probed using this technique. So this is how using quantum tunneling technique, images can be captured. So, for example, this is one of the graphene deposited on a substrate. So you can see the graphene. So it is having honeycomb structure. So at room temperature, you can see that image, that carbon atoms, wherever carbon atoms are there, you can see that kind of bright spots. So compared to other regions. But when you, if you wanted to have a better picture, you have to reduce the lattice vibrations. So because we are not getting the better picture in the room temperature, that is because lattice gets vibrated. When you are at room temperature 300 Kelvin, 300 Kelvin is a thermal energy to the lattice. How do you sense that? How do you get the better image when lattice is continuously vibrating? You cannot get, right? So then when you cool this material to the low temperatures, then you will see this better picture. So this is a measured at 77 Kelvin and this is measured at room temperature. This is how you can get better pictures when you go to the extremely low temperatures. Then you will avoid the all kinds of vibrations coming from the atoms. So this is how one can see the direct uh, direct lattice and the kind of some 2D structures or layered structures one can probe them. So this is the end of the scanning tunneling microscope and X-ray diffraction. Okay. So if you have any questions, please let me know. Any questions?
Sir,
Yes, 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 yes. Please ask me. Yeah. Hello.
sir, audible by voice, sir.
Yes, yes, you are audible. Yes, please tell me. Something is cut in between. Yeah. If you have any question, please feel free to ask via audience. Yes.
Sir, one question will be asking, sir.
Yes, yes, please.
What type of crystal, single crystal or polycrystal, and must be preferred for device fabrication?
Okay. So device fabrication, it's depends on the kind of application you want. So, for example, almost all your mobiles and integrated chips, all are embedded on the wafers of the silicon. Okay, this is the silicon which has been used very I mean very rigorously. So this is the one silicon almost has been used in all the devices. For example, if you go to the solar panel, so there are different types. Again, some people have been using silicon type, some people are using cadmium sulfide type. Okay, so that is depends on the application. Suppose if you wanted to see the piezoelectric effect, for example, what we have seen in this scanning tunneling microscope, where whenever the tip senses the extra voltage, it is moving. That means there is a piezoelectric effect. That means if it senses electric field, that position of the tip is moving. Okay, that piezoelectric effect. For sensing the for piezoelectric effect, you need quartz crystals. Okay, so depends on the kind of crystals, but different depends on the kind of application those crystals can be used. Okay,
Okay, thank you, sir. Sir,
thank you.
one more question, sir. My sir.
Yeah.
How we can determine the non-cubic crystal structure Miller indices, sir?
Okay, so this is a very good question. See, we have a limitation. So until cubic structure, you can do with pen and paper. Okay, so there is a structure factor. Okay,
Okay, sir.
structure factor. For example, let me open the slide and show this. So when you are where you as you are going from cubic to tetragonal or orthorhombic, even worst situation, triclinic, monoclinic, it is not possible to do with pen and paper. There are very efficient softwares are there, foolproof. For example, that is a free software. It is available. So that using that we can able to refine the structure. Okay, so for determining the crystal structures, so again single crystal XRD, all these things are useful. Okay, for example, let me draw here. For example, so lattice constant, let us say uh, distance between two planes is equal to 1 by root of h square plus k square plus L square by A square. So this is the typical distance for the cubic crystals. Okay. So another way to say A is A by root of h square plus k square plus L square. This is the one. So this D is determined from the 2D sin theta is equal to n lambda experiment. So this is Bragg's law. So lambda we know, and n is equal to 1 for the any kind of experiment. So from the theta, one can estimate the d. Once you know d, then ratios of these two can be estimated. This is how A and HKL simultaneously can be estimated from the cubic lattice. Suppose if you take a orthorhombic lattice. So orthorhombic lattice, this formula will not work anymore. Okay, orthorhombic lattice. So you can see d is equal to 1 over root of h by a whole square, k by b whole square, L by C whole square. So like this way, so more parameters are there, more complications will come into the picture. So if you can able to write a program based on based on the starting elements, you will be able to calculate. If you go to the triclinic or monoclinic, there are 6 parameters. A, B, C, comma. Definitely with pen and paper, you will end with a lot of errors. If you can write a program with this kind of equations, one can easily find A, B, C, alpha, beta, gamma. So the example software is foolproof. It is easily available. I mean, software one can download and learn. YouTube many lectures are there how to write structures using proof. So one can easily find out the parameters of non-cubic or any complicated lattices. Okay. Any questions?
Sir, for non-cubic crystal structure, any formula will be determining, sir?
Yes, I have
Like the
shown.
trigonal and hexagonal.
Yes, I just show this. Did you see my slide previously? Have seen? Can you see the slide now?
Okay. Yes, sir.
Yeah. Can you see the what I have been writing? So
Here, empty line will be there. We will draw the one line, sir, only.
yeah, I have written. Yeah. So that is the thing. So this is a formula. So distance between two planes in the orthorhombic crystal structure, for example, that is a non-cubic, that can be determined using this kind of formula: h by a whole square, k by b whole square plus L by C whole square. So this is how non-cubic structure also can be determined using this formula.
Okay, sir.
Yeah.
Thank you, sir.
Okay. Right. Okay. So any further questions?
No question, sir.
Okay. Then I will go to the another part. So far we have seen the crystals, how to grow the crystals, what are the applications, we have briefly gone through it, how to determine the crystal structure, that means how to understand the X-ray diffraction with respect to the direct lattice. So they are connected each other invertly, and so on we have seen. Now we will see if you have a crystal, how to do the properties, how they are distinguish each other. Then I will just to quickly give another characterization tool apart from the X-ray diffraction and FESEM. So for example, magnetic measurements. So this is one of the physical property. Once you know crystal and crystal structure, then at the end you must know more details about that properties. Then one of the property I just chosen here, magnetic property, that can be measured using vibrating sample magnetometer. So this is the one another important characterization tool. Here I will show the working principle of the this instrument called vibrating sample magnetometer. This one, first, I would like to give the content, how I will give the presentation. So first I will give the working principle of VSM, vibrating sample magnetometer. Okay. And then some of you might be familiar with magnetism. I won't discuss much about magnetism but how this vibrating sample magnetometer will measure the real-time magnetic properties, how the properties can be distinguished each other. We can go through this kind of properties using this instrument. Okay. So now let us see first magnetization. suppose you take any material, if you apply magnetic field, then its magnetization gets increased. If the magnetization increased, then you can say there are intrinsically some magnetic moments associated with the atoms. So as you are increasing the magnetic field, magnetization also increases. So this is how you will say that it is a magnetic or diamagnetic material. So these materials, uh, suppose if you wanted to say it is a magnetic material, for example, iron. Whether iron is a magnetic material, answer because iron pieces will not attract each other. Then immediate conclusion is that iron is not a magnetic material, but it's wrong. Iron is a strong ferromagnetic material because of the bound effects. Domains are oriented in different directions, so it exhibits the effective magnetization as 0, but still it is a ferromagnet. Some materials domains are oriented very particular direction, they exhibit permanent magnetic moment, so those are permanent magnets. So for instance, bar magnet teacher, that means iron is a material, okay, ferromagnetic material, that too. So but without using even in the case of iron, there is a difficulty of telling that it is a magnet or not. But some paramagnets, for example, hardly there is no magnetic moment at all. How do you find them? So that there should be a instrument, very sensible instrument. It should be able to measure this magnetization. Okay. So in this talk, I will briefly talk about the working principle of one instrument, that is called vibrating sample magnetometer. This vibrating sample magnetometer works based on the Faraday's principle. Okay, let us recollect what is Faraday's principle. Suppose you take a bar magnet and you move the bar magnet into a circuit where circuit have a coil and that is connected with some small ammeter where it can senses the current whether it is passing through the circuit or not. So when you place the magnet close to the circuit, then it won't have any sense in the metal. So, but when you move the magnet, push towards the coil and take it out, then you will see some kind of current in this one. But this current appears only when magnet is moving here and there. When magnet is placed inside also, it won't have any effect. But when it is placing outside also, it won't show any effect. But when it is moving here and there, then only it is showing the current. That is some induced current present in the circuit. That is because of this Faraday's principle. So what Faraday's principle says, rate of change of magnetic flux induces the electric current, like induced EMF. So this induced EMF is due to the rate of change of magnetic flux. Epsilon is equal to magnetic flux delta P by T. So something magnetic flux should change with respect to the time. So then only induced EMF is a very temporary voltage. It won't last for a long time. This current won't happen for a more than few milliseconds. As long as you are moving the magnet, that means as long as you are changing the magnetic flux, then only it induces the electrical current in that circuit. So this is the basic, using this principle, this vibrating sample magnetometer is built. Okay, so this is in the vibrating magnetometer, what are the elements are required? First, you need a magnet. So this is your sample, this is your magnetic material, this red color is the sample. The sample is placed in the some kind of magnetic field, because you need to show that it is a magnetic material. You can increase its magnetization. Then when this magnetic sample is moving up and down, so this is a vibrating head, it is moving up and down. So that means when you are moving magnet up front and back, you have seen some kind of, without touching any wires or any connection. So with a non-contact mode, under the non-contact mode, you have induced the voltage. Similarly, here also, when magnet is moving in the magnetic field, that means in the presence of coils, these are the coils, when magnetic sample is moving, then there will be induced current inside the coils. So this induced EMF will help in finding the property of that magnet. Okay, so this is a simple, very simple technique. Suppose if you use a very large magnet, you will see large current, obviously, because, and if you vibrate very with a high frequency, then also you will see very large current, because d pi b by dt, either you increase the pi b value, or its increment with respect to the time. That means you increase the frequency of your vibration, increase the more induced EMF. So that means it's all related to the intrinsic property of the magnet one can find out. That is what, using this using simple Faraday's principle, this instrument is designed, and under the Faraday's effect, this vibrating samplometer works, and one can determine the magnetic properties of those materials. Okay, this is the one typically how the different type of vibrating sample magnetometers appears. Here is one electromagnet. So electromagnet will produces the magnetic field in this direction. This is where, when a very small rod is there, this small rod is going inside the placed in the inside the magnetic field, and when this rod is vibrated using this vibrator, this is the vibrator. So we're up and down, there will be induced EMF inside the coils. Coils cannot be seen here. That induced current will calculate the magnetization like this way. Okay, this is how different varieties of instruments are there in designed on this different type of like one is Lakeshore magnet, another is PPMS, quantum design, and so on. So this is how this vibrating sample magnetometer works. Then why we are learning about this instrument? Because it has a connection with the your crystal crystal and its characterization. For example, if you have a crystal, how these properties are found and everything you can see from here. Okay, for example, if you have a paramagnet, the susceptibility versus temperature looks like a simple paramagnet, 1 over T behavior it shows. If you have an antiferromagnet, there is a kind of magnetic transition. Below the temperature, it shows the antiferromagnetic ordering. Above, it is paramagnetic. Below the antiferromagnetic transition, it is antiferromagnetic. Okay, and ferromagnetic mechanism also one can see. At high temperature, it is paramagnet, obviously like that of antiferromagnet. But when you cool, it become, all the movements are ordered ferromagnetically. It become like a ferromagnetic order state, like exactly like how if you cool the glass of water, it become ice. Same way, if you cool the paramagnet, it becomes like a solid. Okay, so this how magnetic materials are characterized. But how, if you wanted to learn about more details about these magnetic properties, one must have a crystals. If you have a crystal and orient the crystal in the magnetic field direction, let us say this is the magnetic field direction and the crystal is oriented in this direction, then in different directions, okay, this is another orientation. Different orientations gives you different varieties of plots. Okay, so for example, susceptibility versus temperature plot, you can see at a high temperature in the paramagnetic region, for all H parallel to A, H parallel to B, H parallel to C, all three directions do not have any distinction, because it is a paramagnet, or anyway it is a disordered state. It won't have any distinction. But when it is entered into the antiferromagnetic region, okay, when entered into the antiferromagnetic region, different directions shows different values. Particularly H parallel to A, it shows a very wide increment, from it start from 0 and all the way it is increasing to the maximum value. Whereas H parallel to B and H parallel to C almost independent of the temperature. So this information, H parallel to A, H parallel to B, H parallel to C, from this what you understand, there is a easy way of easy access is there. that is H parallel to A having the some kind of special axis that is called easy axis. Along the A direction, these movements are oriented. Okay, that is how you can able to find if you have the crystals. Whereas you can see the average effect from the polycrystal sample. This fellow, you can see this fellow is the average of these all three directions. From the average value of all these three, like polycrystal samples, you will not get any more information. Okay, you understand? So if the advantage of the crystals in the real time physical properties, if you have a crystal, you can able to measure in different directions. From by measuring different directions, you will be able to determine what is the orientation of the your magnetic moments. So here you can see crystal structure is like this way. So A, P, C it has. Okay, so this is the crystal structure where along the A direction, maybe let us say this is the A direction, this is B direction, and this is C direction. So you have the measurement along the H parallel to A, H parallel to B, H parallel to C, all three you have. But H parallel to A movements are very much distinct each other. That means along the A direction, okay, along the A direction, these movements are oriented like this way. Okay, so these are atoms. These movements are oriented in this direction. Okay, they are antiferromatically ordered only, but this along the A direction, you can see this kind of orientation only. Okay, so this way. So okay, so this is how one can able to understand the uh, basic basic properties of the materials using if you have the crystals rather than this boring polycrystalline samples. Okay, this is what I wanted to show the advantage of the single crystals, their growth in both fundamental as well as application oriented and our day-to-day life. So yeah, with this I just would like to close now. Okay, so I still have some more time. You can please feel free to ask the questions if you have anything.
No, no questions, sir.
No
Still now.
questions, huh? Okay, okay. Yeah. So yeah. Okay, thank you very much. So yeah. So yeah, if there are no questions, then can I say bye to you all?
Sir, now it's vote of thanks, sir.
Okay, thank you, thank you. Oh, yeah, yeah.
On behalf of H&S department, today I take this opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today eminent speaker, Dr.B.Koteswara Rao, for accepting our request and for giving such a wonderful presentation on single crystal growth and characterization tools and making event meaningful and interesting. Thank you very much, sir. I would like to express our profound gratitude our principal Dr. Sayed Surya Madam for her constant support and encouragement throughout the program. Thank you, Madam. I would like to extend my heartful thanks to our beloved correspondent Srimati V.K. Padmavatama Madam and our director Srimati V.K. Srivani Madam who has initiated us to this program, her continuous support right from this inception. Thank you, Madam. I would like to express my gratitude to our Managing Director, Sri G. Raghunath Reddy, sir. Thank you very much, sir, for supporting us, guiding us in right way. My heartfelt thanks to our convener, Dr. Haripriya Madam and her entire team, Dr. Jansiran Madam and Mr. Jaiprakash sir and Suman Gopinath Madam and Engineering Madam for this continuous support in making fifth day of this FDP successful. A big thank to Noor sir and Nagendra sir, who is backbone of this online session by providing the technical support. Thank you, sir. Finally, at the end of the session, I would like to thank you all the participants of this FDP for their glorious presence. Thank you, everyone. Thank you, sir.
Yeah, thank you very much, Shivaya, and thank you very much, Haripriya Garu. So, and the entire team from the gates. So hopefully we will meet sometime in either gates at IIT Tirupati. So physically, okay. Thanks.
Okay, thank you, sir.
Yeah, yeah. Bye.
Okay, bye, sir.